I want to thank you all for joining us for today's session entitled R&D Enterprise Architecture for Advanced Analytics and Machine Learning. Next slide, please. Before we get into today's session, I want to do a quick introduction of who Astrix Technology Group is, so you can kind of have a sense of who we are as a company and what we do. First and foremost, we are an informatics professional services and staffing company that's dedicated to servicing the scientific community. Some quick stats about the company. It was established in 1995. It's privately held. It originated from the IT division of a company called APBI, which is a $300 million life science research organization. It operates from 8 offices with over 800 employees today. The headquarters are in Red Bank, and there's 2 divisions. There's a staffing division and a professional services division. That's who you're talking to today. We'll talk a little bit about those services in just a moment. We target Fortune 1000 life science companies, government, research institutions with large and fast-growing IT staffing and compliance needs. The mission of the company is and always has been to deliver scalable, sustainable solutions in IT and staffing for the scientific community. A little bit about the professional services. It's an end-to-end plan that covers the entire life cycle of scientific data systems. And this begins with business process analysis, which is ensuring that your informatics projects are going to meet your needs. It then moves into the enterprise architecture, ensuring that you begin with the right designs. And then finally, help with the lab technology selection services and the development and implementation of those systems. Then, of course, it moves into the validation and then the laboratory system services, which can be everything from training to upgrades to support of the hardware and the software. And then there's staffing. We can help staff the individuals to maintain and manage those systems, as well as just staff the scientific personnel in your laboratories. Eventually, this rounds out with a solution that we help you evaluate, implement, and manage to overall enhance the collection and processing of your scientific data. Now, as far as today's session goes, I want to introduce our speaker. Dave Dorsett is going to be your presenter. He brings over 3 decades of experience in R&D informatics throughout the global pharmaceutical, chemical, and consumer good industries. He has an extensive track record in architecting and designing and delivering commercial and in-house informatics solutions across the R&D spectrum. And this is from early research through late-stage development and manufacturing. He is very knowledgeable. I've had a pleasure of sitting in on many of his presentations, and I think you're going to enjoy the content for today. So again, I want to encourage you to ask questions as you go, and then Dave will field those hopefully at the end of the session. Dave, I'll go ahead and pass it to you.
Okay. All right. Thank you very much. So long title for the webinar today. Relatively short agenda slide to sort of go along with that. So today we're going to speak to you all about the architectural aspects around the use of data science, or the interest in data science. And this is definitely a very hot topic. It's been so for the last year or so. So this is something that's on the forefront of lots of folks' minds. We're going to spend a little bit of time just doing a little bit of background and talk about some of the goals and challenges of application of advanced analytical or AI/ML techniques in the R&D space. And then move on from there to talk about, just sort of step back and look at some of the underlying themes and some of the requirements that these efforts actually have in the organization, and talk about like suggestions basically for building out data science capabilities. As I said, this is a relatively new, well, in some ways, which we'll talk about in just a moment, not so new, but certainly a relatively new buzzword of interest. And what I have at the end here is sort of some of the tips and suggestions that I've come across in working with folks to begin to develop sustainable data science capabilities, at least across the spectrum of R&D. So hopefully this will engender some questions as well. And my goal is that everybody sort of gets something out of this to take away from today. So that's hopefully in line with everybody's expectations. So a little bit of the background first. So AI, ML, and scientific R&D, so artificial intelligence, machine language. So we all know, has been discussed over and over and over again for the last decade or so about the explosion in data. And really, there's been an ongoing interest during this whole period of time that we've been automating things and building deeper analytical devices and platforms to study problems at a deeper and deeper scales about what we can actually do with that data beyond just maybe the singular experiment that we're particularly focused on in the lab at that time. So there's been a lot of discussions and a lot of initiatives, and I've spoken before about structuring your data for reuse and the ability to sort of fairize it, which means making the data findable and accessible to people in its principles sense, and that's sort of one avenue, if you will, of interest and pursuit, essentially, to go along with this explosion of data. A little different topic, sort of related to that explosion of data, but today we're going to talk about the potentials for, and I put this in quotes here, analytical use of the R&D data. And we'll talk a little bit more about what that means in just a moment. But here we're going to actually look into, from the point of view of the overall systems and from the point of view of the systems and data architecture, use of the R&D data, which sort of stems from the history of the role of high performance computing as being a key linchpin in molecular biology, and the development of the sciences of related sciences in molecular biology. I mean, the computing aspects of genomics and proteomics, et cetera, were critical, to the beginnings and the nascent, development of that space. So that really, was a lesson in a lot of ways for a lot of folks about what the power of computing can actually do when applied to laboratory data. And then in the bigger world outside of R&D, we all know from our daily life that email spam filtering, recommendation engines, i.e. Netflix and Amazon, et cetera. We have image and speech recognition capabilities that I think 20 years ago we would have just found what we experience now between Siri and Alexa and all that. It's just absolutely astonishing that we would be in this place. So obviously huge amounts of interesting progress in these spaces, fraud detection, manufacturing lines that use visual inspection in an automated robotic way. We have autonomous navigation now. I mean, there's just been so much tremendous development in and around the use of ML techniques, in particular, advancing these kinds of capabilities, and all of that has been sort of the background, if you will, for this interest in what can we do, with these types of techniques as applied to an R&D environment, and that's sort of what we're obviously going to be talking about today. If you go back a little bit, there's lots of different ways of sort of slicing this up in terms of how the various usage or things that fall under sort of this very general umbrella of advanced analytics, AI/ML. From a technique perspective, there's sort of the four domains here of more classic techniques that I would put things into. There's a lot of gray area between these, and that is a constantly evolving form of gray area as we sort of hybridize, elements from one aspect of things to another. But originally, we all, obviously we all scientists, we were all trained in statistical analysis and the ability to, understand significance of results and do experimental planning from a statistical standpoint around hypothesis generation and hypothesis provability and all those types of classic statistical techniques. Statistics obviously, evolved tremendously over the years, Bayesian inference models and all sorts of developments in that particular space. But the general goal of the statistical space, the way I would think about it from this type of categorization, is you're trying to build an inference from samples of your data, build an inference that's relevant to a population, I should say, more specifically from samples of your data. Data mining was a hot topic back, well, a while back. It was one of our buzzwords that we spent a lot of time using and talking about, and so today, we look back, we sort of have now more or less categorized the general field of data mining as, our goals were to discover patterns, unknown patterns, of course, within the data itself. So there's that, and there's still a tremendous amount of work going on in the statistical and data mining spaces. Just because they've been around for a while does not make them less interesting. They're just sort of less buzzworthy. buzzword worthy these days. The newer frames of this now, machine learning and artificial intelligence, AI has been around for quite a while. It's had its ups and downs as a technology. Here are the general categorization that I'm attempting to use in this discussion is, from a machine learning perspective, we're really attempting to develop algorithms to reproduce knowledge from the data. In particular, those algorithms are ideally self-emergent, so they're not pre-programmed. They actually emerge from the data. They are ideally, set up in such a way that they improve as they are used, as they are subsequently trained. It's generally the phrase that's being used there, and so they are basically deeper processing in some ways than just pattern recognition. But really, attempting to develop a computer-based assistant, I guess, if you will, from the data itself. The general area of AI, sort of, again, these terms have a lot of gray area in between them, and lots of folks, from a broader sense, the overall field of AI applies to generalized learning. So rather than learning within a specific domain or a specific data set, which is generally the scope, the way that machine learning is scoped. We're talking here about the ability to learn as well. So we're talking about symbolic reasoning, probabilistic, human-like behaviors. You don't know it, but you know something that's related to it, and you extrapolate that learning into a new space. That's left in this category these days, generally categorized as AI. Overall, the term that's emerged now is data science. That sort of covers all of this, all of these ways of using data reusing data, I should say, to gain more from it. One of the terms that I prefer to use more sometimes is digital science. You'll hear me use both of these terms probably today. We'll talk a little bit more about that as we go on now. So a little bit of background. So current AI ML applications within data science, kinds of things that are being done within the scientific R&D space. These are some examples of the types of things that are now either in relatively common use amongst various places. Not all of these techniques are clearly used in all places, but this is just a smattering of some of the applications of these techniques from statistical data mining, ML, et cetera, that I'm aware of within sort of this overall, obviously pharmaceutical focused R&D is sort of what I'm sort of keying in here. Although, like the last couple, toxicity and material property predictions, that's certainly not limited to pharmaceutical. There's a lot of folks in the general chemical space, petrochemical refining, catalysis, et cetera, space, who are doing a lot of interesting things within the property prediction, physical property predictions. But these are the types of things that people are doing today or have done and either published on or spoken about at various conferences, applying these techniques. This is some set of examples. So some of the challenges of digital science. So it's not all rosy, I mean, there's definitely interesting things that have been done, interesting applications, and in a wide swath of the work that we do within the pharmaceutical R&D process. But some of the things that we are constantly challenged with in this particular space, we have bias in our data. In ML techniques, where your training set that you choose to use to develop the algorithm, as opposed to the data sets that you're actually using to try to produce results with the emergent algorithm, obviously bias in your data is a significant concern. There's lots of different types of biases that can be of concern. Obviously, the fundamentals of it are, being able to select a representative data set of the space that you want to apply the model, that is. So bias, is a constant battle in all of these techniques. It's a battle also from a pure statistical perspective, obviously, too. Solving the wrong problem or resolving the problem, this happens a fair amount. You dig into the data, you apply these techniques, and you realize that what you come up with is an interesting set of conclusions. However, it's not necessarily representative of the problem that you're actually really attempting to solve. So you wound up with information that you clearly already knew, Nothing new essentially was really brought to the table as a result of applying these techniques, or you ended up with a solution that just was clearly okay. The machine centered in on something that was not actually the problem that I was actually out to describe. And sometimes that's related to the data bias and the training set problems. Sometimes it's related to other structural things, and we'll talk more about that in a moment. Lack of explicability of results is an interesting one. We're certainly used to, from a computer science point of view, we're used to writing algorithms that have predictability to them. They take certain inputs, they provide certain outputs. Their expectation is provide output, and that is a fundamental part of how we test software. We write requirements, we create data structures and algorithms to process that data, process that data, expecting it to lead to certain results, and we test against those results. With emergent algorithms and some of these techniques here, there isn't necessarily always sort of the transparency, if you will, of how the machine actually came up with that model, and that can be challenging in certain types of applications in particular. So you wind up sometimes with a model and the inputs that it's sensitivity analysis on how it's assessing the inputs, and it's just you're sort of scratching your head wondering, how does this actually work? The connection between the inputs and the outputs is less than obvious, and that can be challenging to the application of a model in particular. And then a big one in these techniques, particularly ML techniques of whether learning based, is we feed them a training set, we develop the algorithm, we test that algorithm, for success against success criteria, and we deploy it in a situation where the data that we're feeding it, unfortunately, is not within sort of the scope of the training set, and we're really forcing the model to extrapolate. ML techniques are not good, generally speaking, at extrapolation. They're good at interpolation, and so forcing extrapolation, one of my favorite websites to visit, XKCD, contributes the comic here to the right about what happens when you take extrapolation a little too far. So that can happen quite easily with models once they're deployed, once they're attempted to be used in the real world. So these are all real fundamental challenges within the space. Some of them are sort of intrinsic to some of these methods. Others might be things that we can begin to address with some of the things I'm going to talk about in just a moment. Excuse me. So back a little bit again. So obviously we're trying to do here, back to those examples, and the reason for all this interest is we're trying to create models of one form or another that automate and help us optimize our results of R&D. So classic examples, are being able to describe things that happened in the past, pull out the important characteristics that caused or were related to a particular result. So if we can understand what the significance of certain inputs actually are in terms of outcome descriptively, that could help guide us in the R&D process to making better decisions about what experiments to perform, what directions to go, those types of things. We also, ideally, we would love to have the crystal ball, predictive likelihoods of the future. We'd love to be able to, on the basis of a small number of experiments, make a determination about the likelihood of success with a particular problem, whether it be a synthetic kind of problem or a material science problem or what have you. We would love to be able to have some form of a predictive likelihood. Don't waste your time going down this avenue because that small molecule is never going to be a stable formulation in that particular direction. So predictive likelihoods of the future that's sort of one of the big driving forces here. A newer category of model benefits that's been being discussed recently, and there's some folks that argue this is just a form of predictive models, but this is kind of this notion of prescriptive plans of action. So this would be variant of predictive, but here what you're being told by the model is you are likely to be better off if you take the following course of action. So based on past information, the model might be able to give suggestions about, based on past successes, and past failures, things that you could do or not do that would be more likely to improve your outcome. It's this variant of the predictive, flat out predictive likelihoods of the future, but it's really more about the process and the selection of the direction of where to go than it is necessarily straightforward prediction. So those are the types of things that we would really love out of our models. And again, the phrases that our folks are using to sort of coalesce all the goals here. We talk a lot about digitization projects and digital transformation projects and digital science and data science. And these are the buzzwords that are flying around now about this. And really underneath this is this goal of moving our R&D organizations from running on email and phone calls and Excel to algorithm assisted. Flat out running on algorithmics and automation to be able to do directed synthesis on its own, for example, to try to reach a synthetic target. Very interesting sorts of things. In general, in the industry, full-blown running on algorithms is a little bit of an oversimplification, and it's really the goal is really that again, making more use of our data. We collect tremendous amounts of data. We really want to try to be data-centric. Folks do talk a lot about wanting to be data-centric, wanting to be digital organizations, want to run with algorithms basically as assistants to the scientists. So these are the things we're really trying to do. And so now what we'll do is step back for just a moment and talk a little bit about, come back to some of the things I've already touched on and talk a little bit about the nature of digital science, because that'll have an influence then on how we might go about thinking about this. Has a big influence on how you might go about actually doing this work. Okay, so digital science is science. It is experimental. It is hypothesis-based. It is not engineering, and this is something that actually does cause confusion. When we're exploring and applying, this is why I prefer the term digital science to data science in some ways. It is we are employing techniques where we do not know what the answer is going to be. We are trying to collaborate, with an algorithm or within the development of an algorithm. It requires a tremendous amount of flexibility and the right way to frame a problem and good ways of evaluating the success or not success. All the things that we would do in classic laboratory bench scale work. We have a hypothesis. We design our experiments in a certain way. We carry out those experiments in a controlled way to make sure we're testing the hypothesis, assessing those results, assessing our progress towards the hypothesis or not, and really then iterating a lot. And that is the fundamental classic bench science process. So oversimplified, but still. And that is the fundamental idea here of digital science. In software engineering, classic sort of software development engineering, we know what we're trying to build. We have a level of specification of what it is that the system is intending to do operationally. It's a question, and an engineering point of view, how to do it best, right? How do you build the system that will meet those requirements in the better possible way? So here, we don't know where we're going to wind up. We have a goal in mind, certainly. We're going to be testing ourselves against that goal, but we don't have a what. And that is one of the fundamental natures of digital science. And again, the kinds of things that we get into here as you look at the goal that you're trying to accomplish and the different techniques you can use and what your data looks like, which is all things we're going to talk about. One of the sort of sidelines here that that is an interesting set of discussions on its own, right? Is the ability to distinguish correlations from causations, and that's another one of these ongoing things, and that has a lot to do with model weaknesses as well. So a lot of our models, by their nature themselves, are correlation oriented, not causation oriented, and that goes back to that point I was making about extrapolation and proper understanding of your data and all of that. So why all this? So obviously digital science is all about data. That's what it eats for breakfast, that's what it produces, that's everything about it, right? It's all about that data. This, however, is not data in the sense of the way, for example, I've talked in other forums about data, in sort of the sense of the data of the data in the sense of like integrating our systems and conforming to regulatory requirements around data quality and those types of things. We're going to touch on that in a moment. It's not sort of the traditional use of data here that we're talking about. It is fundamentally the same data, but we're talking about actually trying to use it in a little bit of a different way here. So in digital science, to use this sense of data, there's a couple of interesting architectural challenges. The biggest one is that, to a large extent, if we're trying to build these algorithms to assist us in our work and in understanding our data better, the application really is not the center of the world. It's the data that is truly the center of the world. And what we want ideally is data that is not bound by our applications. It survives an application lifecycle. So you place a LIMS system, you bring in a new ELN, all those types of things. From a digital science point of view, that stuff should be irrelevant. And there's a kind of this interesting global trend that's happening in the application space, where applications becoming more and more transient. Consider how many different, the life cycle of applications on your teenager's phone, is amazing. Things come and go. People move readily between application spaces, and sort of that. I don't envision that kind of level of turnover would happen in an R&D environment for a lot of reasons. But one of the big challenges in digital science or in these digital transformation initiatives is actually getting the cultural background and understanding to the point of understanding it's really about data, and it's not about applications, and it's not about systems. We all when pushed, especially, we all revert to talking about systems. It's easy to talk about your favorite ELN or why you don't like that LIMS system or why this one is better, those types of things. In the space of trying to apply these techniques in digital science and data science, that's really irrelevant at the end of the day. And moving this mindset to a data-oriented mindset is a huge cultural problem. It's not actually it's got technical aspects to it. It's a much bigger cultural problem than it is actually a technical problem. So let's talk a little bit more about the characteristics of data. Sans application, pure data. So these are the types of things we would want. And this isn't necessarily a full list of the requirements of the data that we want to be able to use with these in these ways and with this technique. But we want our data to be self-describing. We want it to have the proper context. And that where did it come from, when, who the basic sort of W's, but also richer context in terms of things like relationship between the analytical method and the results themselves. So the context in an R&D environment is a very complex web of relationships, but it's an important aspect to being able to understand our data and being able to then going back to understanding the significance of the models that are actually produced, being able to diagnose what's going on there and understanding whether or not you've got something that could actually be more broadly used and broadly deployed. This contextual information is really, really critical. We want representations to be easy to consume. We don't want to work hard trying to crack apart, very odd, dense, inscrutable representations of the actual data. We want simple access, basically, to the underlying data. we want to have provenance. That's a specific form of context, but provenance is a key aspect here. We want it to be complete. I put an asterisk there, so I'm going to talk about this in just a moment again. But in general, we really, completeness of the data, accuracy, reliability, authenticatability. I mean, for those of you who've worked in, depends on what your background actually is, but you can see there I'm kind of almost touching on Alcoa or Alcoa Plus, and that's why the screenshot on the right. I mean, a lot of the things we need from our data in digital science overlap very strongly with data integrity, compliance, Alcoa Plus, types of concerns that the regulated portions of our industry actually work in, the people that are responsible for producing the experimental information that's eventually summarized into these filings. So all of the backing information essentially that behind a filing for the regulatory agency purposes, or pretty much all of that applies to data within the data science realm as well. So I'm sort of suggesting here something around, in some practical sense, which is that, I think for those of you who are interested in really wanting to push data science initiatives forward, I might suggest that there's a potential for an interesting partnership with the folks who are embedded or interested in data integrity and data quality concerns at your organizations. You have common interests at heart. Are in and around the data. You want to use the data in a different way potentially, but there are some underlying common interests at heart that I think are interesting to potentially explore. Okay, a little bit more about those comments about applications versus data. In the ideal world of constructing these systems that we're going to apply sets of algorithms to and generate the models that we were talking about earlier. We're really talking about being able to move tremendous amounts of data from the application space, so the quote unquote raw data world. And in our case, in these labs, that's a pretty generally speaking, that's a pretty wide variety and diversity of systems, with a lot of overlapping between them. We're trying to move that into some sort of a space where we can operate from, where we can use it to train models and use it to evaluate models and do model developments and then turn models loose. We're trying to move this raw, unnormalized, overlapping, siloed sets of data from applications that, by and large, aren't necessarily transparent with how they store their data and aren't necessarily well supportive of externalization of their data. They have a sort of a locked-in data model. They don't necessarily document their data models. They may have odd choices about their data models. And this is a huge challenge, actually, in application of data science broadly within the R&D spectrum. Generally speaking, you'll get a lot of vendor resistance when you try to get into the data behind the scenes at times. I have worked with people who have had very difficult discussions with vendors about underlying access to the data, and that's both with systems that are deployed classically on-prem as well as systems that are deployed in the cloud as well. Not all vendors, are fully supportive, let's say, of the transparent access to their data, as fully supportive as we would like them to be. Again, you have you're all over the map with compliance to best practice data models. Some of our systems, their underlying architecture, their data models, were literally designed decades ago. So from the point of view of current best practice, they are not necessarily there. And that can be very challenging. To unpack that data that's is locked in the application, because you can see it through the various user interfaces and reports and those types of things, but actually being able to get at it, to be able to combine it with other data sets, et cetera, can be very, very challenging. One of the other things, which goes back to the comment I just made before about changing to a data-oriented culture as being a critical part of enabling data science at a larger scale, is that I don't see enough of people really being explicit about the data requirements as part of the IT systems process. So, when we write system requirements and put out our RFPs and do those types of things, we say a lot about the system must, the system shall, and it's not that those are things you shouldn't be doing. You absolutely need to be doing that. Those are targeted requirements at the work processes, the support of the work processes and operations that are necessary. But we're not as explicit sometimes, or in most cases, frankly, as I frankly would really like to see us start to be about the data requirements. So being really clear about when we evaluate systems and bring them in about what our expectations are for what a sample means, for what a result actually means, and what data what elements of that data we expect that system to be able to maintain and produce and provide access to. I'd like to throw this out to folks, and a lot of folks I'm working with, have been working with recently and working with now. This is something I'm really trying to help folks with understanding the potential importance of this. Back to the fact that the application lifecycle is getting shorter. You really need to be focused on the long-term value of the data that's actually happening here. I think we need to be more disciplined, become more disciplined about elaborating our data requirements as part of these processes. Some other aspects of challenges with like bringing our R&D data together in such a way to use it within digital science, as part of digital science, part of data science. Comparability of results, comparability of data is a huge one. We don't necessarily have, compared to images on Google, right? Google photo images or speech that Alexa has heard or things like that. Our data sets, by and large, are not necessarily big, quote unquote, big data. I don't really care for that particular phrase, but we frankly have a lot of smaller data sets. When you start to combine them, then that's when things get more interesting from sort of the big data or model building kinds of perspective. That opens up the challenge of how do we, if you've got 3 limb systems or a LIMS and an ELN even, and you've got data that's spread across those systems that you're attempting to actually bring together as part of an exercise to feed to a model to generate, predictive or descriptive outcomes, how do you merge that stuff together? This is a huge, actually a very, very substantial challenge. And some notes here, there's a really subtle things that actually happen here. This existence and equivalence are not exactly the same. So you might have 2 systems or more than 2 systems, depending on your company, that have results that might be a percentage of the total that's percentage high molecular weight. And what does that mean? Is that actually comparable? Can you take data labeled the percentage of high molecular weight products from 2 different systems and actually treat those as comparable things? Are they the same? Multiple systems store peak table. That's an even more complex problem, because then you have peak naming issues, and you've actually got deeper, you got mathematical issues around the peak analysis. There's all sorts of interesting things that kind of get in the way of understanding equivalence and comparability. So our structured expression of these equivalences is really definitely a struggle, and worked with a lot of people who have been working really hard on these types of problems. It's not impossible, and definitely progress is being made, but it is an interesting, it's not necessarily per se part of quote unquote digital science from a model building perspective, but it is an important essentially prerequisite to being able to bring together sufficient quantities of data in a lot of spaces. Again, back to that comment about big data, lots of small data. in a lot of our world, we have the way we would get enough diverse data to be able to be certain about the scope that we're training a model against is to combine data across systems, across scales, for example, from high throughput experimentation through bench scale pilot plants. How do you do that kind of stuff? So how do you really know if 2 lots are of the same, 2 samples are of the same material? How do you know if 2 results are really comparable? This is a deep challenge, actually, in many ways. Another big challenge, of course, is the quality of the data itself. I mentioned a little bit of this before when we talked about the requirements of our data. But generally, you know, we'd love to have, I think that should say objective data quality. However, you know, practically speaking, we don't necessarily always need complete objective data quality when it comes to our, you know, the data that we're using. So with respect to the hypothesis and the model you're trying to build, you may not need accuracy or precision to the same level that other problems might need it. The presence or absence of a component may be sufficient if you're trying to build a model of how impurities affect stability. You know, it may be, it may not be, right? I mean, could be threshold levels, et cetera. But in those cases, the exact weight percent or what have you to an accurate degree that would be as something that you would need to put into a filing, that may not be necessary from a digital science model building perspective. So that's the subjectiveness that I'm trying to refer to here about quality, the general space of quality. Another interesting aspect of using data for these purposes versus other purposes is that, you know, we're taught a lot about outliers, how to handle outliers and how to treat outliers with all sorts of statistical based rules, et cetera. From a model building perspective, they can be much more important than the way we treat them essentially classically. Again, back to that comment around extrapolation, discarding outliers, sort of the extreme behavior can make the world too nice from your model building perspective. And so treatment of outliers with respect to building data sets for data science is a real, you know, is a very different thing. We have classic notions of data quality. For example, we use referential integrity, and our systems are designed to say, you know, you always have to have a sample ID. The sample ID has to be unique for every result in a LIMS system, et cetera. Those aren't necessarily sufficient when it comes to bringing data together across systems. And so our classic notions of data quality, referential integrity being one of the tools that we use to ensure data quality within a system, they aren't necessarily completely sufficient when it comes to, you know, when it actually comes to what we're trying to build here to feed and generate models. So we need broader notions of how systems are related to each other in order to be able to going back to that problem around joining data again. So understanding non-equivalent necessarily or non-exact match, you know, types of relationships in bringing together data across systems that's another deep challenge. The other comment I'll make here is that, and this is well known and sort of codified in all the sayings about, you know, data scientists spend 80% of their time or budget in cleaning up data. Passive data quality is not a scalable thing. So classic data cleansing or quality exercises or where those you know, those types of sayings come from. You know, if we're really attempting to build our systems in such a way that we can use the data to do these types of higher level analytical techniques, we have to be better about our data quality, and that again goes back to data architecture. Passive after the fact data quality assessments just will be throwing money at them forever. So my hope is that, you know, we can continue to evolve and find better ways of doing deeper active data quality that is actually inter-system types of data quality problems and not just intra-system. All right, lots of challenges, lots of background. What are real things that I've seen people doing, and what can you actually do? Obvious one is to seek parts of the organization of an R&D organization where the data problems we've just been talking about are more limited, right? So some places where that occurs are there's consistency needed for regulatory reporting, so everything funnels through one fundamental LIM system, for example. So there's the process itself, because of regulatory pressure or because of internal harmonization of processes and systems, the data itself has fewer of those types of comparability problems that I was speaking to. Still may have to address comparability over time, depending on how long of a period of time the data was, you know, the data of interest is actually generated within. You still might have those comparability problems, but they might not be as extreme as some of what I was speaking to. So there might not be big data here, but it could be very usable, and you can use it to very productively. I know folks have very productively explored techniques in the model building space against different types of data by focusing on in these subset areas. Again, smaller amounts of data, so that has some relevance to training, how you train and what models you select and what technical things you do, but still useful without sort of opening all the Pandora's box of some of the data problems that I was speaking to. And there's some aspects of it, just some hints around approaching data sciences projects in a collaborative sort of way. So the work that you might do if you're interested in applying these types of techniques to a particular domain, assessing and profiling the domain, looking at the data, trying to really assess its relevance to the problem you're trying to solve, right? To the goal that you're trying to build an algorithm for. It may turn out that when you step back from that and assess it with the domain in mind, and that's very critical, because that's key to being able to evaluate whether or not you're going to be successful. It's not the technical aspects of a model, but the scientific aspects of the outcome of the model. You may have a really interesting problem, look at the available data and what shape it's in and whether or not it's going to be relevant to the problem, and you may honestly need to step back and say, I don't think there's not a high likelihood of this data being able to help in this particular problem space. That doesn't mean, then my suggestion is that doesn't mean to just completely walk away. Catalog that, what you found, etc. Share it with other folks trying to do this. There are definitely other problems that that data could actually be relevant to. But checkpointing this practicality thing is a really important thing before you get into sort of the classic filter, cleanse, prepare, transform model, etc. type of things. So again, finding spaces where some of these data challenges are more limited is useful. Collaboratively approaching these projects is another sort of very, very much a thing that you can do now inside your organizations. For bigger problems, really moving towards this discipline of a data architecture, which is a major cultural shift. Building a blueprint for your overall R&D data, not operationally focused, like I spoke about, not three-letter acronym oriented, but actually, what are the key entities essentially that are key aspects of the data. And I'll speak just a little bit more to that in a moment here. This is not about tools and systems and about building a quote unquote data lake with this technology stack or that technology stack or warehousing or marketing, or it doesn't have anything to do with these technologies. This is a discipline and architectural kind of thing that's independent of a lot of these kinds of things. Really trying to create a data supply chain, right? And a good understanding in the R&D organization from a scientific process point of view, how data is being used. And the best tips that I have for this is it's a little to take a backward sort of approach. We're used to modeling data sort of in this motion of conceptual to logical to physical, or we're used to modeling data from the point of view of the people who produce data. The most practical way to begin to create a real data architecture for these kinds of applications is to work backwards from the way we think about data, not from the point of view of the creation of the data, but from the point of view of what does the data describe? How is it actually used, right? Then work backwards toward the way it's actually produced. It also helps you focus on a practical scope, because we do produce an awful lot of data that may or may not be relevant in the sense of how it's used. This isn't like a concrete where you're never going to just completely only worry about the data that's actually used. There's very important context, at least in the way that data is actually produced. But from a prioritization point of view, this is a handy way to think that I found to think about how to begin building a data discipline inside an organization. Some other last tips here on how to really sort of move forward on an enterprise R&D data architecture. There's a technique in software development, software engineering called domain decomposition. You can Google this. Bounded contexts. This is a way of breaking down a problem. So, classic analogy is how to eat an elephant. So establishing these bounded contexts is really a very helpful way to think about how to break down these big data problems into pieces that you can then, actually rationally sort of consume and manage. Be careful about jumping to storage models and finding yourself in the details of certain approaches to tools like ER diagramming I'm not saying that ER diagramming is bad. I'm saying that from the point of view of developing a data architecture, trying to do it on the basis of ER diagrams for all of your systems and all of your key data packets and everything, it's not going to scale. You have to have a higher level sort of domain schema oriented approach in order to be able to address a bigger R&D or R&D wide process with these kinds of things. The connections between the domains, I mentioned this before, in the area of comparability and quality. Those domain connections are really, really important. And it's important, again, because we're trying to build helpers, right? Out of these models are sort of essentially helpers for directing what work we're doing, how to understand the results of what we've done in R&D. Stick to scientific language for creating and documenting these data structures. They need to be vetted and explainable, consumable in the language of the domains that are involved. So scientific language, and specific to, if you're trying to solve, if the problem's in drug product formulation stability, then it needs to be in the language of that work, and not really in a technical language. That's the domain aspect of digital science is really, applying data and becoming a digital organization, isn't about removing the domain knowledge. It's about augmenting the domain knowledge of your scientists. And so turning this into a technical problem in general is not going to be, sort of directionally, as impactful as it will be, keeping it really a scientific, a domain-driven problem. Okay, so those are some final practical tips on sort of dealing with some of these enterprise data problems to feed these goals of building data models and such. Oh, okay. And that's the end of my prepared material. So I turn this back for a moment and grab a drink of water. And
Thanks, Dave. Much appreciated. That's great content. And I guess as we get ready to kind of wind down, there will be a few questions on the floor that have come up. But I want to point out that right now, Astrix is presenting a complete webcast series with thought leaders from the lab informatics industry. This is going into November. And the next one is tomorrow. It's going to be a session called Embracing the New R&D Paradigm with Structured Data and Insights. This is tomorrow at 1 p.m. And it's going to feature the LIMS vendor Benchling. So we're pleased to be presenting that tomorrow. We encourage you to go out to astrixinc.com right here. And you'll see right on the homepage a blurb about that session. You can also find it within the blog section of the website. You'll also have received an invite for that too, just by virtue of being on today's session. So be on the lookout for that, and we certainly hope you'll join us for that session. And you can go to the next slide.
Sure. Oops. Come on, Nels.
With that, we'll go ahead and stop the recording.